Welcome to our video on using derivatives to determine the shape of a graph. So let's recall that an increasing graph will have a positive slope. So for increasing left to right, your slope is positive, so the sign of your first derivative will be positive. So that would look like this, uphill. If you have a decreasing graph, you would have a negative slope, and the sign of your first derivative would be negative, so that section of graph would look like that. So we can use the first derivative test to determine whether a critical point, c f of c, is a local minimum or a local maximum on the graph. If the first derivative changes from positive to negative at that critical point, then that point is a local max. If the first derivative changes from negative to positive at your critical point, then this point is a local minimum. Let's see how that looks on a graph. So in this graph, we can see that we have an uphill section from here to here and another uphill section from here to here. In both of these green sections, your first derivative would be positive. You have an increasing section of the graph. In this middle section, you're going downhill from left to right. Your first derivative would be negative. You have a decreasing section of the graph. So we can see at this point here, we're switching from increasing to decreasing, so we have a local max. At this point here, we can see we're switching from decreasing to increasing. Here we have a local min. So that's your first derivative test, looking at the sign of f prime to determine whether you have a local min or a local max at a critical value. Now in this graph, we've got several different things going on. So I've color-coded it according to green being increasing and pink being decreasing. So here we have a critical value where f prime of a is undefined, so we could have a vertical tangent line here. Here we've got a critical point where we've got a horizontal tangent line. Same here, horizontal tangent line. Same here, horizontal tangent line. At this critical point here, we're going from increasing to decreasing, so I would have a local maximum. At this point here, I'm going from decreasing to increasing, so I would have a local minimum. And here, I'm increasing, and then I'm still increasing, so I have neither a local max nor a local min. At this point here, going from increasing to decreasing, I have a local max. So now we'll talk about inflection points and concavity. First, some definitions. An inflection point is where the second derivative has a zero value. So a point where the second derivative changes signs, either from positive to negative or negative to positive. So we say the concavity switches from down to up or from up to down. We'll look at some graphs of this in a second. So if you're concave upward, your second derivative is positive. All right, we don't necessarily need to talk about the tangents to the graph, but this will be shaped like a smile. If you're concave downward, your second derivative will have a negative value, and this will be shaped like a frown. So looking at this graph, this pink section right here is shaped like a smile. This is concave upward. This green section is shaped like a frown. This is concave downward. Right here it switches from concave upward to concave downward. We call this the inflection point. So when the second derivative switches signs, it instantaneously will have a value of 0. So we solve for our inflection points by setting the second derivative equal to 0 and finding those x values where the second derivative is 0. Those are your inflection points. So when the rate of change of your slope is positive, that means the second derivative is positive. That means your slope is going from being negative to positive. so you're increasing the value of your slope. So you have a positive rate of change of your slope. Second derivative is positive. When we say the rate of change of our slope is decreasing or negative, that means you start out with a positive slope, you gradually go to 0, and then you go negative. So our value of the slope is decreasing. So that would indicate a negative second derivative, concave downward. So inflection points can look different on different graphs. So here are 3 instances where you have a second derivative equal to 0, but you have a different shaped graph. Notice that the tangent to the graph in this graph here has got some positive slope. Here it's got a 0 slope, and here it's got an undefined slope. But nonetheless, you've got a second derivative equal to 0 in all 3 of these cases, which indicates that you're switching concavity at that inflection point. So you can see here we're going from up to down, here we're going from down to up, and here we're going from up to down. So there's different ways that this might look on a graph, but nonetheless your second derivative is switching directions. So what we have is that the signs of the first and the second derivative indicate the shape of a section of a graph. So I've labeled these 4 graphs in terms of their concavity. So if you have a smile, a positive second derivative, you're concave up. So here's 2 instances where I've got a positive second derivative here and here, and I'm concave up. In these 2 instances here, your shape is a frown. You've got a negative second derivative, so you're concave down. So then you could take a look at the sign of the first derivative. In this first graph here, I'm going uphill over this entire section. That means my first derivative has a positive sign. In this graph, I'm going uphill as well over the entire section. This one also will have a positive first derivative over this entire section of graph. Here I'm going downhill, so negative first derivative, negative slope. Here I'm going downhill as well, negative first derivative, negative slope. So you can see that the signs, we've got positive, positive. So I'm talking about second derivative, first derivative. Here I've got negative, positive. Here I've got negative, negative. And here I've got positive, negative. So the combination of the signs of the first and second derivative tell you what the shape of the graph is in that section. And we're going to use this knowledge to find the shapes of certain graphs. So let's talk about the second derivative test. This is a test that is used to determine whether you have a local max or a local min at a critical point. So the second derivative cannot be 0, and it must be defined at this critical point. Then we can use it to determine whether you have a local min or a local max. So if, on the other hand, your second derivative is 0 or undefined, then you wouldn't use the second derivative test to conclude local max or local min. You would go back to using the first derivative test, which we talked about earlier. So if f prime of c is equal to 0 and f double prime of c is not equal to 0, we know for sure that we're not talking about an inflection point, that we're talking about either a local max or a local min. Recall that when f double prime of c is equal to 0, we have an inflection point. All right, so an inflection point can have a horizontal tangent line which has a first derivative equal to 0. So we've ruled out that these are inflection points that we're talking about. So if f prime of c is equal to 0, then you're talking about either this situation or this situation. All right, so if f prime of c is equal to 0 and you have a positive second derivative, then you're concave upward, you've got a local minimum. If f prime of c is equal to 0 and f double prime is negative, then you're concave downward, you have a local maximum. So sometimes a second derivative is a quicker test to determine whether you've got a local max or a local min, but it's equally as valid to use the first derivative test where you're examining the sign of your first derivative to determine whether it switched directions from negative to positive or from positive to negative. Either the first derivative or the second derivative test are valid ways to determine whether you have a local max or a local min. So we're going to learn how to use calculus to create a graph of a relatively complicated curve. So the first step would be to find the first derivative and locate the critical values, which we already know how to do, and we can plot these points. Next, we'll take the second derivative, set that equal to 0, and locate the inflection points if we have any of those, and we'll plot those points on the graph. Then we'll determine asymptotes and draw those with dotted lines. Then we'll plot any other useful points, such as the intercepts, so the x and y intercepts, and any other points that we need clarification on where the graph goes, and we'll put those points on the graph. Next, we'll set up a table of intervals using a number line, where on that number line we've placed the critical values and the inflection, the x values where the inflection points occur, and we determine the signs of the first and second derivatives within these intervals. So we'll fill in a sign table. Then, using what we know about concavity, we'll determine the concavity case for each of our intervals based on the sign of the second derivative. And taking all this together, we'll be able to sketch the curve within these intervals according to the signs of the first and the second derivative. So we're going to do a couple examples using this procedure. So example 1 says, make a table, v-table, and sketch the curve of this cubic function here. So the first thing we're going to do is take the first derivative and set it equal to 0. To find out what our critical values are. So I can divide by 3. And then I could factor this. If you can't factor it, then you would have to use quadratic formula. So I can see that I've got 2 critical values for this function here. Now let's take the second derivative of our function. So if I go back up to this right here, I'm going to take the derivative of the first derivative to find the second derivative. So that would be 2 times 3, 6x minus 12. So I'm going to set that equal to 0. And I'm going to solve for x in this case. X is equal to 2. So this means I have an inflection point at x is equal to 2. Now I'm going to make my number line, scoot this up, and on my number line I'm going to put on these 3 values. So I've got 1, I've got 2, and 3. This would be negative infinity, and this would be positive infinity. Now I'm going to divide up these sections of the number line like that, and I'm going to choose a test x value within these intervals, and I'm going to find the sign of my first derivative in each of those intervals and the sign of my second derivative in each of these intervals. And that's going to give me enough information to help me sketch my graph. So the test x's that I choose are 0, 1.5, I'm choosing any arbitrary value in between these values on my number line. It doesn't matter what you choose, so hopefully the easiest one possible. So let me also label on my number line, this right here was the value where f prime was equal to 0, so that's a critical value. This was my value where f double prime was equal to 0. This is my inflection point. And this one over here was also f prime is equal to 0. So I like to label that over my numbers on my number line. Okay, so now what I want is pluses and minuses in my table. So I take, let's look at this row in the table first. I'm trying to find the sign of the first derivative for each of these test values here. So that means I got to go back up to my first derivative. My first derivative was right here. And then I plug in these x values into my first derivative, and I figure out what the sign is, and I write that in my table. So this video doesn't get too long, I'm going to tell you what I got. I got plus, minus, minus, and plus, and that was just simply substituting my test values into the first derivative right here and getting a sign. The magnitude of the value I don't care about. I care about the sign, not the actual value. I'm going to do the same thing for my second derivative. So my second derivative equation is right here. So where my x is, I'm going to put in my test value, and I can figure out what sign I get out of that. Now I did that already, and I'm just going to tell you what I got. Like I say, I don't like these videos to get any longer than necessary. All right, so now I have my table of signs. And this is what I'm going to use to sketch my graph. All right, so the next thing I want before I go any further is I want to figure out the y values for my points on my number line. So let's go ahead and do that. So I've got another blank slide which I'm going to go to, and you have one in your packet in your handout, and I'm going to make that table over here so I don't run out of room on that page. So I went ahead and I figured out the y value for x is equal to 0, 2. That would be my y-intercept. So I'm going to get 4 dots. All right, and then I'm going to be able to put these on my graph. So substituting those into the function f of x, I can get these y values, which I already calculated. All right, so now I'm going to make a little sketch and see what the shape of this graph looks like. So I'm going to divide my x into units 1, 2, 3, 4 here, and I'm going to have a different scale on my y-axis so I can get some definition. Let's say this is 35 and this is 30. So this is not going to be super to scale, but we'll get an idea of our features of this graph. So now we're going to put on these 4 points. 1, 2, second point, that would be 232. Third point is 330. All right, so we have 4 points here. Now I'm going to go back and look at my concavity cases as well as what I know about my end behavior. So first let's look at our interval between negative infinity and 1. I'm going uphill from left to right, and I'm concave downward. So that would mean my graph would look like, so that's all the way, so I'm going to have to go through this point here. So I'm concave downward and uphill slope. So I've got that piece on it. It had to go through the y-intercept. Remember, this is an x cubed function, so this is going to make sense. down, up behavior. We would expect it to look like that. So that's the left piece, the left interval. Next, in my interval between 1 and 2, I'm negative slope, downhill, and concave downward. So that would mean negative slope, concave downward. That gives me my shape. Now, between 2 and 3, I'm switching concavity. I've got an inflection point. I'm going from concave down to concave up, but my slope is staying negative. So that's between 2 and 3. Negative slope, concave up. So negative slope, concave up. So that was an inflection point right here where we switched from concave down to concave up. So that should hook together better here. But let's just fix that a little bit. And the last section of my graph is from 3 to infinity. Here I'm going uphill, positive slope, and I'm concave up. So positive slope, concave up. So that takes care of my end behavior, matching down, up, down, up. And this is concave up, positive slope. So now we can take a look and see if we can justify the fact that this looks to be a local max. Of course, this was an inflection point. So I'm just going to say this is your inflection point. This looks to be a local max, but we can verify that either using the first derivative test or the second derivative test. This looks to be a local min. So if indeed the first derivative test told us this was a local max, we would expect positive slope, negative slope. So we go back here and we can see positive slope, negative slope. Now if this one is a local min, we would expect negative slope, positive slope, go from the left side of 3 to the right side of 3. All right, so that would be here. So negative to positive, yes, that worked. And then we could also look at our second derivative test. So negative means concave down, so that's the local max. Negative, concave down, local max. Positive, second derivative, concave up. So that both the second derivative and the first derivative verify local max and local min. Okay, so we finished that example. So here's another example. So we've got a more complicated function. So we got to take the first derivative. So let's rewrite it as x times x squared plus 4 to the 1/2 power. All right, so we're going to do this analytically, of course, which is what you're going to have to do on your next quiz. So we all know that graphing utilities exist in the modern world, but the ability to determine the nuances of a graph and the shape of a graph using calculus is a very important skill to develop. So we're going to develop this skill from the ground up here. All right, so now I'm going to find f prime of x, first derivative. So I've got the first times the derivative of the second chain rule plus the second times the derivative of the first, which is 1. So I can cancel these 2's out here. So I've got x squared divided by the square root of x squared plus 4 plus the square root of x squared plus 4. Well, let's get a common denominator here, because we're going to have to take the second derivative and we need to get this simplified. So this is x squared plus radical comes off now here, and now I've got one denominator. So this is 2x squared plus 4 over root x squared plus 4. Right, so this is my first derivative here. Now I need to set that equal to 0 to find out my critical values. That means my numerator must be equal to 0 in order for that function to be equal to 0. All right, so that means 2x squared equals negative 4, or x squared is equal to negative 2. However, I'm going to get non-real numbers if I take the square root of negative 2. All right, so we get non-real solutions here. That means we have no critical values. Okay, so no critical values. Now let's take the second derivative and find out whether we have any inflection points. So we're going to use the quotient rule on the first derivative. So we've got the bottom times the derivative of the top minus the top times the derivative of the bottom chain rule divided by the bottom squared, which would just be x squared plus 4. So now we simplify this. So we've got 4x times the square root of x squared plus 4. All right, we've got some 2's we can cancel here. So then we've got minus 2x squared plus 4, and there's an x as well, divided by the square root of x squared plus 4. So that's just my numerator. So let's put back on here my denominator so I don't forget it. Let me just put it over here. All right, that's my denominator. Now let's multiply this here piece by the square root of x squared plus 4 over the square root of x squared plus 4. So I'll get 1 over x squared plus 4 times 4x, and then we said, let's just write it out so there's no confusion about what I'm doing here. I'm multiplying that by I'm trying to get a common denominator. And then this is minus x times 2x squared plus 4. Okay, so now I've got multiplying this together, the radical will come off there. So I'll have my denominator, which I'm keeping out here for now. So this would be 4x times x squared plus 4 with the radical off, minus x times 2x squared plus 4, but I have now only one denominator. All right, so we're getting there. So simplifying the numerator, I've got 4x cubed plus 16x minus 2x cubed minus 4x divided by, now let's put this both down here in the denominator. All right, now it looks like the like terms in the numerator will be 2x cubed plus 12x, x squared plus 4, square root of x squared plus 4. So set that equal to 0, which means the numerator must be set equal to 0. So I've got 2 x cubed plus 12x equals 0. So that's the same thing as saying x cubed plus 6x is equal to 0. If I factor that, I'll get x times x squared plus 6 is equal to 0. So that would be x is equal to 0 would be one inflection point. X squared is equal to negative 6. I'm going to get non-real again here. So that won't be anything. So I've got one inflection point here, and that's x is equal to 0. All right? So I have no critical values and one inflection point. So now I'm going to draw my number line. So I've got 0, and then I've got negative infinity, positive infinity. So now at that point 0, my f double prime is equal to 0. All right, so now I want to get my test x, and then I want to find the sign of my first derivative and the sign of my second derivative. So I can just pick negative 1 and 1. All right, so now I take negative 1 and I plug it back into my first derivative, which was here. So I already went ahead and did that, and I'm just going to tell you what the signs are. I got plus plus for both intervals. Positive first derivative for both intervals. And then next thing you're going to do is you're going to take your test x's and you're going to plug them into your second derivative. Let's highlight that. So there's my second derivative, and when I plug my test x test both of them into that, I get negative and plus. And you always want to be sure that when you say you've got an inflection point, that your sign switches signs. If it didn't happen, you made some kind of a plugging in mistake, most likely. All right, and I didn't have any critical values. You can see my sign of my first derivative is not changing, so that makes sense. All right, so now we'll go ahead and we'll go to the next page and we'll plot some points. So my only critical point on my chart there was my inflection point, but let's get some more values. Let's just go to the left. This is somewhat arbitrary, but I don't want just one point in my graph. All right, so I want to see what's going on with this graph. So if I plug negative 2 into f of x, I get a decimal number approximately negative 5.7. And this is just so I can get a sketch. If I plug 0 into my function, I get 0. If I plug 2 into my function, I get 5.7. All right, so now let's look at the concavity. So I know I've got a point negative 2, negative 5.7. Let's just say it's down here. And then I've got the point 0, 0 at the origin. And I've got another point that I'm plotting, which is positive. So this is symmetric about the origin here, right there. All right, now let's go back and look at my concavity intervals. So between negative infinity and 0, I'm uphill, concave down. Uphill, concave down. All right, and then looking at my table, between 0 and positive infinity, I'm uphill, concave up. All right, so I've got that inflection point for sure. So this is my inflection point right here. And I'm concave up from negative infinity to 0. Concave down and then concave up. All the while I'm uphill. All right, so I don't have any local maxes or local mins. It's almost similar. It's similar to the shape of a cubic graph, but we had our original function, of course, was this with the square root in it. Okay, so we did it. We've got all of our analytics. We've got our sine table, and we've got our sketch. All right, back to another polynomial here, next to the fifth polynomial. First step, we take the first derivative. So that would be 60x to the fourth plus 180x cubed minus 600x squared. Set that equal to 0. Well, let's just put that up here. So if I divide out by 60, I'll get x to the fourth plus 3x cubed minus 10x squared is equal to 0. Then I'm going to factor out an x squared. And I can see that that's factorable. 2 and 5. So 5 minus 2. So I've got x is equal to 2 here. X is equal to negative 5 here. And x is equal to 0 here. So these are going to be my critical values. I've got 3 critical values. Now I'm going to find the second derivative. So I go back to my first derivative here before I simplified it, and I find that's before I set it equal to 0 and divided out that common factor. I got to go all the way back to here. Now I'm going to find the second derivative. So the second derivative is 240 x cubed plus 540 x squared minus 1200 x. Now I set that equal to 0. So I can divide out by 60 here. So I'll end up with 4x cubed plus 9x squared minus 20x is equal to 0. Let's factor out an x. So that's 4x squared plus 9x minus 20 is equal to 0. Now that is not factorable. So I can see that I'm going to have one critical value here. And here I'm going to have to use quadratic formula. Let's go over here. So I've got x would be negative 9 plus or minus square root of 9 squared 4ac 2a. So I'm going to get 2 values from that. So I'm going to get 1.378 and negative 3.628. All right, so I've got 2 more inflection points. So this is an inflection point. And these both here are inflection points. All right, so now I set up my number line using all of these values. So I'm going to put them in order. So I've got negative 5 then negative 3.628, then 0, then 1.378, and 2. So on the top, I'm going to say this is where f prime, let me just put, I always like to put this on top, helps when you're analyzing what's going on in the intervals. Right here, this was where f prime and f double prime were 0. Here, f double prime is 0, and here, f prime is 0. All right? So now I've got my intervals. So this is a fifth order polynomial, so we can have more things happening as far as ups and downs in the graph, right? So this is your f prime sine and f double prime sine. This is your test x. All right, so the test x's that I'm going to use are -6, -4, -1, 1, 1.5, and 3. All right, so that means I'm going to plug in all those numbers into my first and second derivative, and I did that already, so I'm just going to tell you what happened. All right, so I get these signs, and you got to make sure that it's switching concavity. When you're talking about an inflection point, your sign has to switch for your second derivative. And you got to make sure that happens. And when you're talking about first derivative, your first derivative sign has to switch. All right? Well, it doesn't have to, because I see right here that this is going to be a flat spot. All right? Right here, it's switching. Where it doesn't switch, that's your inflection point. All right, we got enough information now to sketch our graph. So I took my values from my number line, I put them in the x column, I subbed them into f of x, and I got my y values. These are going to be the points I'm going to put on my graph. So I'm going to make a scale 1, 2, 3 here, like that. All right, so this would be -5 all the way over to here. Now, so I've got -5. I've got some very high value here, so let's just put that up here. So this is not going to be to scale in the vertical direction. And then here I've got -3.6, and then I'm down somewhere from that original high value there. And then I'm at 0, 1. And then I'm at 1.3, -300. Just relatively speaking. And then I'm at 2, -495. All right. So now I want to connect this graph somehow based on what I know from my chart. So looking at the first interval between -infinity and -5. So between -infinity and -5, I'm uphill, concave down. So uphill, concave down. Now between -5 and this was -3.6, I'm downhill, still concave down. Now between the next interval, between here and 0, I'm downhill, concave up, downhill, concave up. All right. And then the next interval between 0 and 1.3-ish, here to here, I'm downhill, concave down. All right, and then the last interval, well, the interval between 1.3 and 2, I should say, that's this one here, downhill, concave up. So smile. And then the last interval is between 2 and infinity. I'm uphill, concave up. All right, so that's the shape of my graph. So this was my inflection point here. There's another one here and another one here where the second derivative was 0 and the concavity's switching directions. Now this should be a local max, and we can verify that using the first derivatives test or just looking at the concavity. So between, see, here's where my extreme value would be. I'm going from positive to negative, or I can just look at my concavity. It's concave down, so that means it's a local max. And then if I look at my other critical value where the first derivative is 0, I could see I'm concave up on both sides. So that tells me, shaped like a smile, this is a local min. And this is an x to the 5th polynomial. So that's down up. And we can see the end behavior was down up. Okay, so we did that one. So here's a rational function. So we're going to do this. We know something about these already. So they've got vertical asymptotes. So when the denominator goes to 0, you've got a vertical asymptote. So I can see that occurs at x is equal to negative 1/4. And then you've got a horizontal asymptote. When your degree of your numerator is equal to the degree of the denominator, you ratio the leading coefficients. So I've got y is equal to 1/2. All right, so negative 1/4 is a domain restriction. So x cannot be negative 1/4, hence a vertical asymptote. So now, if I find the first derivative and the second derivative, which I've already done using the quotient rule, we get this for our first and second derivatives. Now, in order to find the critical values, I find the values of x that cause f prime to be 0. So I have a constant in the numerator, so there are no values that will cause this to occur. And then the other possibility is, what are the x values that cause f prime to not exist at all? Well, the only value would be negative 1/4, but that's not in the domain of the function. So therefore, I have no critical values. Now let's look for inflection points. Taking a look at the second derivative, I want to find x values that cause the second derivative to go to 0. I have a constant in the numerator, so this will not go to 0. So I have no inflection points. So the x value of interest is x is equal to negative 1/4. So I put that on my number line, and that's my vertical asymptote. So I'm interested in seeing what's going on to the left and to the right of my vertical asymptote. So my test x's that I'm going to use are negative 1 and 0. Subbing into f prime, my signs are negative and negative. Subbing into f double prime, my signs are negative and positive. All right, so now I have enough information to see what's going on with my graph. So I know that my vertical asymptote is negative 1/4, and my horizontal asymptote is y is equal to 1/2. So I'm going to sketch those in using dotted lines. So there's my asymptotes. Now I picked a few points, easy points here, so I could get some dots on my graph to get it more accurately drawn. So if I substitute negative 1 into my original function, I got a y of negative 2.3. So 1 dot here, and then 0, 9 is my y-intercept. So 1 dot here, and 1 I substituted into my original function and got 2.2. So I've got a dot here. So the indications are that I'm going to be up here and down here with some x-intercept over here somewhere. But let's look at the concavity and see if that justifies our hunch. So going back to the table, to the left of the vertical asymptote, I've got decreasing slope and concave down. So decreasing slope and concave down. So that would indicate that I'm going downhill and I'm concave down. So I'm going to go through that point, head for the asymptote. To the right of the asymptote, I'm going downhill and I'm concave up. So I'm going to go through these 2 points, downhill, and I'm concave up. All right, so I've got an pretty accurate sketch of this rational function using what we know now about concavity and slope. So now let's look at example 5. So I've got a function to the 2/3 power. So I went ahead and found the first derivative and the second derivative. And I'm going to look for my critical values first. So I'm going to set this equal to 0. I have a constant in the numerator, so I'm not going to have a critical value due to the first derivative equaling 0. However, if x is equal to 4, then f prime of x, f prime of 4, does not exist. So this also is a critical value, right? So I have one critical value, x is equal to 4, because my first derivative does not exist at x is equal to 4. Now looking at f double prime, I could say the same thing. I can't get this function equal to 0 because I've got a constant in the numerator. So that means I have no inflection points. All right, so let's go ahead and set up our number line. So we have 1.4 that we're interested in here, and that's where f prime does not exist. All right, so if I make my table, I've got 2 sections of my table. So I've got my test x, and then I've got my f prime, and then I've got my f double prime, which I'm going to find my signs for. All right, so my test x that I'm choosing, 0 and 5. So I plugged them in, and I got negative, positive for the first derivative, negative, negative for the second derivative. All right, so let's try making our graph here. Okay, so I've got this value of interest 4, and I don't really know what's going on to the left of 4. So I'm going to pick something really close to 4 just to get an idea, and really close to 4 on this side. All right, so when x is equal to 4, and I go back to my original function, I can see that if I put 4 in here, I'm going to end up with 0. And if I sub in 3.9, I end up with 1.3. and 4.1 also 1.3. So I'm suspecting there's some symmetry involved here with this function. All right, so I'm going to put on my dot at 4, 0, and my dot at really close to it on either side. All right, so then I just want to find out what my y-intercept is. So if I put in 0, I got 15.1. So I got a point up here where it's crossing, roughly there. All right, so now if it is indeed symmetric, you would think that 4 units to the right, which would be 8, you'd also get that same number. So I'm checking it out, and I actually did get that same number. So this function, so this is 8 over here. This function is kind of V-shaped, basically. Now, let's see what our concavity tells you. So if I go back to look at our chart, I'm going downhill to the left of 4, and I'm concave down. All right, so downhill, concave down. And then the other side of 4, I'm uphill, still concave down. So the only way for that to happen is if you come in there at a point there. All right, so this is how your graph is going to look. It's going to come in at a point right here. Now, if you had any question about whether that really was happening, you could keep finding points closer and closer to 4 on either side, and you're never going to get past this. You're always going to be approaching this point here, 4, 0, but you won't get past it. You'll get closer and closer and closer. So this is your classic vertical tangent line kind of a problem. So we actually have a vertical tangent line going on in this problem right here. All right, so concave down, downhill, concave up, uphill slope. And you could get more points in here if you wanted to get an accurate graph, but this is what's going on here. And this is why the first derivative doesn't exist here, is because you have a cusp. So example 6 looks a little familiar. We've done problems like this before. This is a rational function because I've got this -1 here in the power position. So if I rewrite this function f of x, I'll get f of x is equal to 5x squared plus 2 divided by x. All right, so that's just with your common denominator equal to x. So I have a domain restriction. X cannot be 0. So if I have a domain restriction where x cannot be 0, that means I have a vertical asymptote at x is equal to 0. While we're at it, let's talk about whether we have a horizontal asymptote. So looking at the highest degree, in the numerator I have a 2, and in the denominator I have a 1. So that tells me I have no horizontal asymptote. I am going to have a slant asymptote, but I'm going to tackle those in section 4.6. So let's just say at this point we have no horizontal asymptote. Next, let's find f prime of x. And I've done that already using the quotient rule. F prime of x is 5x squared minus 2 over x squared. And I've also found f double prime of x. F double prime is 4 over x cubed. All right, so let's check for critical values. In order to find our critical values, we need to find the x values that cause the numerator here to go to 0, where f prime of x would be 0. So if 5x squared minus 2 is equal to 0, that means that 5x squared would be 2, x squared would be 2/5, So x would be plus or minus the square root of 2/5. All right, so these are my critical values. First derivative would not exist when x is equal to 0, but x is equal to 0 is not in the domain in the first place. And then looking for inflection points, if I set 4 over x cubed equal to 0, since I have a constant in my numerator, I can't get that to occur, so there are no inflection points. Next, I'm going to set up my table, so I need my number line. And on my number line, I'm going to put on my vertical asymptote, which is at 0, and my two critical values. All right, so now I'll draw my table. The test x values that I'm going to choose are -1, -0.5, 0.5, and 1. So then I sub those into f prime and I get plus, minus, minus, plus. I sub those values into f double prime and I get minus, minus, plus, plus. All right, so let's take a look at the graph now. So I'm going to investigate what's happening at my two critical values. Square root of 2/5 is approximately equal to 0.63. So this is negative root 2 over 5, and this is a positive root 2 over 5. Subbing those into my function, I get these decimal values here. All right, so I know I have a vertical asymptote. We said at x is equal to 0, so let's put a dotted line in for that. So now I've got a dot at negative, negative, negative. So 1, 2, 3, 4, 5. So let's say here and there. So I put both of those dots in there. Now we've got to figure out what's going on according to our sine table. So we want to look to the left of negative 0.63. So looking in my table here, that means I've got a positive slope and a negative concavity. So uphill, concave down. And then going back to the right of, I'm in this interval here, between 0 and the first dot, I'm going downhill, concave down, downhill, concave down. I got to approach my vertical asymptote, so this is probably more symmetric than that. So maybe more like that shape. And then if I go to the right of the vertical asymptote, I've got a negative slope, concave up, negative slope, concave up, heading for the asymptote. And then to the right of that, I've got positive slope, concave up, like that. So this is what this graph looks like. Basically, we did say it has a slant asymptote, so it's probably not, it's probably going to go out at an angle like that, but this is roughly what we've got. Pretty close. Like I said, in the next section, we'll tackle the slant asymptotes. So that, looking at the table, we should be able to verify that this is a local max and this is a local min. So a local max would be concave down or slope going from positive to negative. So that concurs. And this one over here, a local min, should be concave up, yes, and slope going from negative to positive. All right, so that's our graph. All right, so I'm starting out by telling you that I already calculated my first and second derivative for this rational function here. If I set it equal to 0, I can find out that when x is equal to 0, my function will be 0. So we might suspect that there might be a value of x that'll cause this denominator to go to 0, in which case the first derivative would not exist. But if you set that equal to 0 and solve for x, you would get imaginary numbers. So the only critical value is x is equal to 0. So for the second derivative, checking for inflection points, if I set my numerator equal to 0, you can see that x squared would have to be 216 over 972. So taking the square root of that, I'll get plus or minus 0.471 roughly. Okay, so I do have two places where I've got inflection points here. Okay, so I'm going to take these three numbers and put them on my number line. Okay, so I've got them on my number line. Now I have to figure out a test x, and then the signs of my first derivative and my second derivative. So the test values I'm using are -1, -0.3, 0.3, and 1. So I plug those into my first derivative and I get plus, plus, minus, minus. And I plug those into my second derivative and I get plus, minus, minus, plus. All right, so let's go ahead and construct the graph now. Okay, so I take my x values that I'm interested in, my 3 x values here, subbing them into my function, I get y values. So I see some symmetry, of course, happening here. So I put those dots, relatively speaking, not super accurate, on my graph. It's going to be symmetric. And then I check to see if I've got any asymptotes while I'm at it. Well, I can see the denominator will not go to 0. We already discussed that, so I'm not going to have any vertical asymptotes. But I will have a horizontal asymptote. See, the degree of the numerator is less than the degree of the denominator. So that's the case where we have a horizontal asymptote of y is equal to 0. All right, so this we know from our prior studies of rational functions. So I'm going to draw a dotted line at y is equal to 0 right now. And of course, what this tells me is that my function is going to approach this horizontal line as it's heading out this way. Okay, so let's look at our table and see what it tells us about concavity and shape. So when I'm to the left, I'm in this interval right here between -infinity and my first inflection point. I'm uphill, concave up. So uphill, concave up. All right. Then the next interval, I am uphill, concave down. All right. Then the next interval, I'm downhill, concave down. And then the final interval, I'm downhill, concave up. Smile shaped. All right, so I'm approaching my horizontal asymptote. So this is what my graph looks like. So this here looks like a local max. This, of course, was an inflection point where your concavity switched. So is this one here. So the local max can be verified by checking to see that this is concave down, or that your first derivative switched from positive to negative. Right, we can see that happening here. Concave down, switching from positive to negative. All right, so we've done that one. Okay, so I found the first and the second derivative of our function here, which has an e to the x, and I simplified those. Now, if I set this first derivative equal to 0, I can see that this part will never go to 0, but this part will. So 2x squared plus x equals 0, or x times 2x plus 1. Whoops. And then I can see I'm going to have x is equal to 0. And I'm going to have x is equal to negative 1/2. So I have those critical values. Now, if I look at my second derivative to see if I have any inflection points, this part will not go to 0. But this part here very well could. I can see that this is going to require quadratic formula. So if I solve 8x squared plus 8x plus 1 is equal to 0 using quadratic formula, I'm going to get that x is equal to negative 8 plus or minus root 32 over 16, which is going to give me x is equal to negative 0.146 and x is equal to negative 0.853. So these are my inflection points. So putting all of these values on my number line in order, I've got 4. So then I set up my table and I choose my x values. I'm choosing negative 1, negative 0.6, negative 0.2, negative 0.1, and 1. And I sub in my test x values into my first derivative. I get positive, positive, negative, negative, positive. Subbing my test x's into my second derivative, I get positive, minus, negative, well, plus, and plus. All right, so now I'm ready to construct my graph. So I take my 4 values and I calculate my y values for these 4 values, and I get those values. Now let's sketch a graph. So I'm going to use this scale. These are small numbers, so I'm going to spread it out. So I'm going to put these values, these dots, on the number line. So the first one is negative 0.853.024. Let's just say it's here, roughly speaking. And then at negative 0.5, I'm up slightly. And at negative 0.146, I'm down even lower than the first one that I plotted. So let's say here. At 0, I'm at the origin. Okay, so let me get 2 points to the right of the origin so I can see what's going on over there. So at 0.25, I get 0.17. So that's higher than anything I've got by quite a bit. So let's just put it there. At 0.5, I'm at 1.85, so it's shooting up here, what you would expect with an exponential. All right, just to get an idea what's going on that side. All right, now let's sketch this in. So you can see the concavity is really going to help with this because this is a strange-looking function. So in my first interval, between negative infinity and my first dot, I'm positive slope, concave up. All right. Now, The reason I'm not going under that horizontal the x-axis is because if you have an e to the 4x or something like that, and you put in a very significant size negative number, you're going to get a value very, very close to 0. And you're going to find that I stuck in negative 100, and I found out that my calculator gave me 0. So it's not exactly 0, but it's very, very close to 0. So it's going to have asymptotic behavior at this axis here, this x-axis. So that's why I drew it like that. All right, and you can always test it. If you're not sure what's going on to the left of your last value, stick something in there and figure it out. All right, now between the negative 1 and the negative 0.5, well, it wasn't negative 1, it was this value. I'm going uphill, concave down. So uphill, concave down. So that means frown. So kind of like that. And then in the next interval, I'm downhill, concave down. Downhill, concave down still. I haven't switched concavity yet. And then in the next interval, I'm downhill, concave up. So I'm starting to smile here. And then I didn't have concavity for those intervals, but if I go back to my table, everywhere to the right of 0, the right of the origin, should be uphill, concave up. So that verifies what's going on with my dots. It's just going to swoop up like that, uphill, concave up. All right, so the scale on this thing is of course off, because I had all these small numbers here that I was trying to get some feel for what was going on. So if you tried to graph something like this, it would almost look pretty flat over here, because there's not very much definition between these numbers. But really, you've got inflection points, you've got a local max, you've got another inflection point. Let's just write that on there. You've got a lot of interesting stuff going on here, where without calculus, it would be hard to tell what was going on here. So this is a local max, and this is a local min. And you can verify that by looking at your concavity number, your signs, and either your first derivative test or your second derivative test. So at this negative point, let's go back here. At this value here, negative 0.5, we are definitely concave down. So the second derivative test tells you that's a local max. At my 0, I'm concave up. So that second derivative test tells you that you're a local minimum. All right, so here's this complicated function here. And we got it all worked out using calculus. All right, so that was a long video. I wanted to get it all in one video so you have the basics. Your homework problems are not going to actually require you to sketch graphs, but we will have to do that on a quiz. But the preliminary work of determining all of the essential ingredients to making a chart are going to be covered in your homework problem. So we should be ready to tackle that.